So this kind of diagram I drew on the previous page is called an energy level diagram, and it is actually really important. It's not just an illustration. It's used in quantum mechanics to describe atoms and their energies and their energy levels, etc. It's used, and even though the Bohr atom is not perfect, the energy level concept is quite good, and is what is used to describe the atom. So this is a quantized atom, and now let's make an electron green, right? So we can say that, okay, so there's an electron that can sit in this energy level, and that is the lowest energy level. It's called the ground state. The ground state, that's its lowest energy level. And we can add energy and excite that electron up to what's called the first excited state. And so then you can imagine from there on, we've got the second excited state and the third excited state, etc. Of course, the first excited state is n equals 2, the second excited state is n equals 3, so you got to be careful about those minus the 1, we're 1 off there. The ground state is n equals 1. We can excite the electron from n equals 2 to n equals 3 and excite it to, and the arrows just indicate we are exciting it, we're adding energy of some sort, right? We're adding energy in to excite the electron, adding energy in to excite the electron. Or we could add enough energy to just push the electron straight up, skip n equals 2, and we can put it into n equals 3. But these are the only allowed states, is the point. They're the only allowed states. It cannot, the electron, if we try to give so what's delta E for this right here? Delta E is equal to, so the change in energy from n equals 1 to n equals 2 is 10.2 eV. So I need to give the electron 10.2 eV of energy to get it up to n equals 2. What happens if the electron is in the ground state, so ignore the other electrons that I've drawn here, and we only have a single electron atom. So I'm just showing the electron as being in any one of these states, not all of the states at once. So let's just say that we are in the ground state, n equals 1 state, right here, and we give the electron 5 EVs of energy, right? You say, oh, well, we bounce the electron up to here, and then what does it do? It just falls back down to here. No, it just doesn't go anywhere. If we give it 5 EVs of energy, that's not enough energy to do anything, and that energy is not absorbed by the atom. That's what's important. The energy is not absorbed by the atom. But if we give the electron 10.2 EVs of energy, then the atom can absorb that energy, and the electron can go up to a higher energy state, up to the higher energy state. Or if we give it however much it takes to get up to here, we can go up there. And if we give it somewhere between 10. What's that difference? 13.6 minus 1.5 is 12.1. I think it's about 12.1 EV. So if let's say we give it 11 EV, if we give it 11 EV, it might be enough to put it in n equals 2, but it's not enough to put it in n equals 3, and so it's going to absorb enough energy to put it into n equals 2, possibly, or it won't absorb anything. I can't tell you what the atom's necessarily going to do, but in order to knock the electron up into a higher energy state, we do have to give it enough energy to get there. Okay, so what I'm drawing here is just the atom is absorbing energy. Where does that energy come from? It comes from the outside, right? It comes from heating it up, adding heat. It comes from electricity, plugging in and putting an electric field across a gas. It comes from adding light. We can shine light on it, right? Like in a photoelectric effect, where we're exciting the electrons in the photoelectric effect to the point where we're releasing them from the metal. In a photoelectric effect, you're actually taking those electrons and you're giving them enough energy to release them. Right? And so we can add any kind of energy to get the electron up to higher energy level. And then, if the electron now starts in a higher energy level, if the electron has been, absorbing energy, the electron has been knocked up to a higher energy level, then the electron can fall, that shouldn't be a wiggle like that. The electron can fall back down to a lower energy level, and if it does, it must release energy, and it is going to release energy as a photon. We've already said this. And the delta E, so the difference in energy here between 3.4 and 1.5 is about 1.9. Nope. 1.9. So it is going to release a 1.9 eV photon, right? So that would be 1.9-ish, whatever 3.4 minus 1.51 is, 1.9 eV. Or the electron is going to go from that n equals 2 state all the way down to the ground state, and it's going to release a photon of delta E is equal to 13.6 minus 1.51 is 12.1 eV photon, right? So that's the hence the line spectra, right? Those are the individual colors that the atom can radiate. Now you might say, all right, so how often does this happen? How often does this happen? And the fact is that electrons change energy states because first of all, we're always adding energy to atoms. It's impossible not to. Radiation energy is all around, and all the other kinds of energy. What are they when you transfer by radiation? I can't remember what they're called, but the different ways of transferring energy. But we can transfer by radiation, we can transfer by electricity, we can transfer by shining a light on it. There's always energy exciting atoms. So the electrons in the atom are continually going up and down and up and down and up and down. And so they're continually absorbing energy and emitting energy. And it turns out that also there's all different kinds of states in atoms, and this is a whole field of physics. But most states, the atoms do not tend to stay in for very long. So you add energy, you're continually adding energy, you knock it up to n equals 4, and it will quite quickly go back down to n equals 1. But there's a lot of electrons, in materials, not in a single atom, because when you're looking at the emission spectrum of a material, you're actually looking at 10 to the 21st atoms, and it's not one atom. So you've got electrons all the time moving up and down between these states. And the movement of a single electron between states is generally, and it varies a whole lot, but like nanoseconds. So if you knock an electron up to the higher energy state by adding a little bit of light, then it will fall back down in a nanosecond. Now interestingly, I'll just take a real quick side here and say there are things that are called metastable states, and they're special states where the electron tends to gather and stay for a little longer. But when we stay for a little longer, we might mean microseconds or milliseconds. We don't mean stay there. And those metastable states are the states that allow us to make lasers. If you can find a metastable state, then you can get enough electrons up into that state before they start falling down, and you can have what's called the stimulated emission of light by the fact that you stimulate these electrons to start falling down, and they are going to emit high intensity light of all the same wavelength. That's a laser. I know I didn't explain that terribly well, but that's actually what a laser is. If you can find a metastable state, a state where the atoms tend to want to stay a little longer. That's why lasers are not easy to make or discover or whatever, because you got to find these metastable states in atoms, which are not very common. Okay, let me just look a little bit closer at this emission of light. So if the electron goes from if it's going to emit light, it's going to go from a higher energy to a lower energy, and the change in energy of the electron is going to be EF minus EI, and that's going to be a negative number. But that means that the photon that it emits is the positive of that, right? Is EI minus EF. That's the energy of the photon that is emitted. Because if we go from 1.51 EVs to minus 13.6 EVs, the electron loses 12 EVs. The photon gains 12 EVs. Hence, the energy for the photon is EI minus EF. That means that HF is equal to EI minus EF, and therefore HF is equal to, so that means we can just plug in, right, that we know that EI equals the ground state energy divided by n squared. EI is the ground state energy divided by n squared. So if we just use the absolute value of the ground state energy, 13.6 EVs, call that E1, and Your book might call it E0. I don't have the book right now, but it doesn't matter. It's just a constant, 13.6 EVs. Take the minus sign explicitly outside, then EI minus EF looks like that. So HF is equal to, we can factor out the E1 and say, okay, so this is the same as 1 over n final squared minus 1 over n initial squared for the quantum numbers of the two states. And we can make a substitution, which you'll see why in a second, that F is equal to C over lambda equals E1 times 1 over NF squared minus 1 over NI squared. And so therefore, 1 over lambda is equal to E1 over HC times 1 over NF squared minus 1 over NI squared. And lo and behold, what is this? Don't know if you recognize it, if you remember. That is the Rydberg constant. This is exactly the line spectra, Balmer series, right? Balmer series and the other, Paschen series, etc. Balmer, Paschen, whatever those series are, ... line spectra. They found out back in chapter 3, they figured this out empirically. Now we've explained it. This is the formula they came up with empirically. It is now predicted by the Bohr atom. Fantastic, Bohr. Now the Bohr atom, even though he hasn't explained why, I mean, he said that the angular momentum is quantized, but he didn't say why it was quantized. It matches observation. It explains everything. So the Bohr atom is now accepted as a reasonable model of the atom. Now, careful, because one of the things that we have allowed here, notice that we've been ignoring Z, but the nucleus can have a larger charge, and we just put a Z in front of everything that had the charge of the nucleus as E, and therefore our energies are Z squared, etc. But the Bohr atom does not properly describe, or it doesn't describe. It actually doesn't describe multi-electron atoms. So it describes all atoms that are atoms with singly ionized, doubly ionized, whatever, ionized to the point where they only have one electron. So it correctly describes atoms with a single electron and as big a nucleus as you want. So the nucleus can be Ze, but a single electron atoms. Single electron atoms. And again, all that means is, physically, that just means we've ionized the atom enough times so that we only have one electron left. So, for example, it's a singly ionized helium atom, a doubly ionized lithium atom, and then what comes, I don't know my periodic table. It's a hydrogen atom, a singly ionized helium atom, a doubly ionized lithium atom, whatever's next after lithium. Be, I think that's beryllium. But anyway, on the periodic table. So the first thing, one proton, this is Z equals 1. Whoops, hold on. Some examples here. Z equals 1 is the hydrogen atom, single proton in the nucleus. Z equals 2 is the helium atom, 2 protons in the nucleus. Helium plus means that it's got a charge of plus 1e. That's what that means. And that means it's singly ionized. There's only got one electron. Z equals 3 protons in the nucleus. So it would normally have 3 electrons, but it's lithium plus plus. That means it's got a charge of 2e, positive 2e. It means it's missing 2 electrons. It's doubly ionized. Z equals 4, beryllium plus plus plus. Z equals 4 means beryllium has 4 protons. Beryllium would normally have 4 protons, 4 neutrons, and 4 electrons. But if we take away 3 electrons, the beryllium has a charge of plus 3e, so that's Be plus plus plus. That is a triply ionized beryllium atom. So this is what is correctly described, and we can go up the periodic table. We don't have to stop at Z equals 4. That is correctly described by the Bohr model. But he doesn't correctly describe multiple electron atoms, and we will get into that next time.